All right, we're at 17.4, resistance, resistivity, and Ohm's Law. Let's go to the, oh, I lost the PowerPoint. There it is. All right. When a voltage, a potential difference, delta V, is applied across the ends of a metallic conductor, as in the figure shown here, the current in the conductor is found to be proportional to the applied voltage. That is, I is proportional to delta V. We can write that delta V equals I times R, as shown up here in the figure. I probably jumped the gun. Delta V equals IR. And in fact, we define resistance as delta V, the potential difference, divided by I. So the voltage divided by current is equal to the resistance. The SI unit is volts per amp, which is equal to ohms. The little omega, I had a physics professor way back that called it omega. Omega, the capital omega, is the symbol for resistance. Ohms, we call it ohms. So many ohms of resistance. Okay, so if you have 120 volts divided by 6 amps, the resistance is 20 ohms. Okay, here's a bunch of different resistors. You already were exposed to some that look, are on the bottom here. The they have color bands. The color bands tell you what the values are. You have if you look at these round tubes, this brown round tube, that's a fixed resistor. But if you look just below it, these other long, they're not as long, but they're brown tubes. You can see that part of the wiring is exposed. And those are variable resistors. And you're going to be playing with a variable resistor when we do Ohm's Law. These that are round with these, you can see the wire around it, those also are variable resistors, and any of these that have knobs are variable resistors. The others are all pretty much fixed. The symbol for resistor is this red, is this zigzag line. It's shown red here. That's how you display it in a circuit diagram. So delta V is equal to IR. That's Ohm's Law. And we can see I think they call these things ohmic when they have this relationship. In other words, if the slope is equal to 1 over R, if you plot voltage on the horizontal and I on the vertical, then the slope is equal to 1 over R, but it's linear. It's linear within a certain range. I mean, if you get too high, then it'll break down and burn up. You can always smell when someone in the lab has burned up a resistor. So be forewarned. If you do, always let me check your circuit before you turn it on. Things that don't have a linear relationship, or I believe they're called non-ohmic. I should make sure let's see. A non-linear current voltage curve for a semiconductor. Oh, this is talking a semiconductor. This is not really a semiconductor. Semiconductor is flat in one section. Anyway, that a semiconductor is not linear, so it is not ohmic. It is not. It's not like a resistor. Okay. Now, resistivity. Now, different materials have different resistivities. Boy, this it's cut off part of the table here. I'll try to fix that. So the table, this is a table right out of your book, the resistivities and the temperature coefficients of resistivity for various materials at 20 degrees C. 20 degrees C being about room temperature. I think when we measured it at about 24 degrees. So you can see there's silver, copper, gold, aluminum, tungsten, iron, platinum, lead, nichrome, carbon, germanium, silicon, glass, hard rubber, sulfur, and quartz. And you can look at the resistivity, ohm meters. Um, Ohm meters. So for silver, 1.59, copper, 1.7, gold, 2.44, aluminum, 2.82. Now, if any of you have ever played with a, I mean, nowadays most of you have laptops. Back in the old days, you could open up your computer. At least I would. Being the geek that I am, I had all sorts of different types of boards, data acquisition boards, timing boards, video boards that we would swap in and out, and we would use, you would see that the contacts were often gold plated, and it's like, well, gold plated, that's 2.44 times 10 to the minus 8. Uh, it's more it has a higher resistivity than silver, 1.59. Yes, but it's not corrosive, and that's why they put gold plated. They often use gold plating on the edge connectors for computer boards and stuff. Now, well, I'm talking back in the 90s and early 2000s when we used to play with, maybe even in the 80s. We used to play with the boards and switch the boards in and out. Anyway, that's why you would use gold instead of silver, which has a better conductivity because it's non-corrosive. And we'll get to the temperature coefficient later on. Okay, resistance is equal to the resistivity. The rho is the resistivity times the length divided by the area. Now, this is going to become important, just like the um, formula for capacitance. Capacitance was equal to, for a parallel plate capacitance, if it had a dielectric, we added a kappa, a K constant. So the capacitance was equal to epsilon 0 times the area divided by the distance separating the plates. That was an important formula for understanding the capacitors in series and parallel. This is going to be an important formula for understanding resistors in series and parallel. So remember this formula. Resistance equals the resistivity of the material times the length divided by the cross-sectional area. Okay, let's, and that's it for this section.